Thank you. Sure. Thanks for the nice introduction. Good morning, everybody. So I'm going to talk about inflation the next 4 lectures. It goes without saying that it's a lecture for you, not for me. Well, I always learn something when I lecture myself, but ask questions during the lectures, okay? You have a period of in the afternoon to go into details if you need, but I don't care if I don't finish my program, okay? I mean, in any case, I will provide notes for the lectures in case you need more detail. Okay, so first of all, let me set the stage with stupid conventions. I'm going to use from now on the conventions, natural conventions. So I'm going to put, for simplicity, C equal 1. I'm going to put H bar equal 1, which will allow me to simplify all the numbers, all the figures that I'm going to tell you. For instance, just let me give you a notation. So the GV to the minus 1, or GV, that I will use all the time, which corresponds to 10 to minus 14 centimeter. And then, for instance, 1 megaparsec, which will be a natural unit for us to use, like the horizon or the size of the current universe, will be, roughly speaking, 10 to the 24 centimeter, just to give you an idea. But I will use the GV or the inverse of it from now on, okay? And I take it for granted that more or less you go to ChatGPT and you find the conversion if you don't remember, okay? Now, I also take it for granted that most of you, or I hope a large number of you, have a background on cosmology. How many of you? Can you raise your hands? Okay, large majority. Okay. How about inflation? How many of you have been exposed to the idea of inflation? Okay, not so many. Very good. Otherwise, I would be boring you for it sometimes. Okay, so so let's start with some plan of the lecture. So, as you know, the subject is inflation. What I will do, I will address kind of a number of subjects, which will be the first one today will be the problems of standard cosmology. Can you see from the back? Is it okay? And then I will, of course, I will go to the possible solutions, which will go, of course, invoking inflation, of course. Okay, there are other ways to solve the standard model problems, but of course, I will focus on inflation today. Tomorrow, I will go to how to realize inflation. In particular, I will introduce the notion of the scalar field. That is the easiest way to deal with a period of inflation. Then from the lecture number 3, and I will say also the number 4, I will go to the most interesting part, which according to my opinion is the most interesting, which is the cosmological perturbations. So I will tell you how to compute the cosmological, or let's say the inflationary perturbation. And I will give you reasons why we believe that inflation is a standard paradigm in modern cosmology. I will try to convince you that, in fact, we have a solid theory to understand the CMB anisotropies and the last case structure of the universe. Okay? So those are more or less the subject that I would like to discuss with you. I guess maybe the first part will be familiar to some of you, and I hope the last part of the lecture will be a little bit less familiar, otherwise it's not that fun. Okay, so let me start from, yes. Yeah, the fourth and the fifth and the fifth, okay. Sorry. Right. Okay, so let me start from the basics, so from the Friedman-Robertson-Walker metric. from which we will discuss the problems of cosmology. So we know that in cosmology we assume that we are on large scale, sufficiently large scales, in such a way that the universe looks homogeneous and isotropic. Homogeneous means that it is similar in every point and isotropic in any direction. So what we do, we introduce the metric, which I write in this simple way, which will also allow me to define the metric and the convention for the signs. So I introduce the scale factor, a square of t times dx square. So it's basically the Minkowski metric, apart from the fact that there is a scale factor. So a of t is a scale factor, which of course is there to take care of the fact that if I have a universe which is expanding or contracting, this function will change as a function of time. So here I'm using the convention with the minus sign. So if I have a Minkowski matrix, I use this convention here. Okay? Just for you to, in some textbook, of course, you have the opposite, but for the time being, we were going to use this. Of course, if I use, so those are Cartesian coordinates. If I use in polar coordinates, the metric, so if I go from Cartesian to polar coordinates, I will have a metric which looks like it's a little bit more complicated. So, well, let me just write down the x squared part. This part remains exactly the same, so I'm not going to write it. So it's going to be dr squared 1 divided by 1 minus k r squared, plus, of course, r squared d omega 2 squared, which is the angle part, which we are not concerned with. The reason why I wrote this piece is because there is this constant k. So k is a constant. It does not change either as a function of time nor as a function of space, and can be normalized to assume plus or minus 1 or 0. Okay, so 3 discrete values. And of course, we will concern most of us with the k equals 0, which is the case of a flat universe, as you know. While plus or minus 1 correspond to a closed universe, like a sphere, or minus 1 like an open universe, an hyperboloid. I'm not going to spend so much time on it because I take it for granted that, that this is something that you know very well. Now, how to find the equation of motion for this scale factor? So we are going to now be concerned about this object here. This object, I remind you, that is not a physical quantity, in the sense that I can change my coordinate system and change this object here. What is physical is ratios of these quantities, as we will see later on. Okay, so this is something important and sometimes is confusing. So how we find the equation of motion for A of t? Well, we go to general relativity, which I also take it for granted from now on. So we write down the Einstein equations. R mu nu minus 1/2 g mu nu times the Ricci scalar equal to the energy momentum tensor times the 8 pi g Newton. G Newton is, of course, the Newton's constant. And then we suppose, like we do because we are using the cosmological principle, we use the fact that T mu nu, the energy momentum tensor, is diagonal. So it's an object which is diagonal and has the following component, rho, 3 times the pressure. So this is the energy density. And this is the pressure density. Okay? Again, I'm assuming the fact that the universe is homogeneous and isotropic, and therefore there are only diagonal terms. Okay? So once I have this bunch of equations, and then I have the energy momentum tensor, which I assume to have this form, you know that I can get different equations. First of all, I introduced the concept, which is very important in the also inflation, the Hubble rate. which is defined to be A dot over A, okay? And the equation of motion that I get are the following. I get that the square of the Hubble rate plus k over a square, where k is the same k that I have here, so it takes values plus or minus 1 or 0, is equal to 8 pi g Newton divided by 3 times the energy density, rho, okay? So that's an equation that is a basic one. I'm going to use it in the rest of the lecture several times. And then I have an equation for the acceleration or deceleration according to the sign that I get, which is a double dot divided by a equal to minus 4 pi divided by 3 g newtons, and then I have rho plus 3p. Okay? And here you see the fact that contrary to Newtonian cosmology, where you will have only the rho here, you get, of course, a contribution from the pressure density, which is, of course, what general relativity tells us. General relativity tells us that any form of energy will basically give a contribution to the expansion of the universe, so you have to also to include this term. In Newtonian cosmology, you don't have it. Okay? So I guess you are familiar with this equation as well. I can rewrite this equation using the first one as the derivative of the Hubble rate, which is minus 4 pi g Newton times rho plus p. You just combine the two equations, taking the derivatives of the first and using the second. So this also, this third equation, I'm going to use it in the following. Okay, so please take notes about it because it's very important for the idea of inflation. Of course, that's not enough. Those equations are not enough because then I have to supplement this equation with the covariant conservation of energy. So the covariant conservation, which is basically the covariant derivative of T mu nu equal to 0, which if I use the energy momentum tensor and the metric of the background, I'm going to find this equation here, rho dot equal plus 3h times rho plus p equal to 0. And again, you see that the fact that I have the pressure here is also fundamental, because as you know, there are, we will be interested, in fact, in two or three possible solutions of these equations. So let me change the blackboard, not just to, so in order, this one. So from this equation, I can now specify what is the content of the universe, and in particular, I am interested in three possible behaviors. The first one is the case in which I call radiation dominated, RD. Okay, is the case in which the pressure of a relativistic fluid, let's say also relativistic, P is equal to rho over 3, or in general, when I define a parameter W, which is P over divided by rho, in this case is equal to 1/3, okay? In this case, rho goes like a to the minus 4, if you solve this equation there, because of course you have rho dot plus 4h rho equal to 0. And remember that h is a dot over a, so it's clear that rho goes like a to the minus 4. In this case, I don't get a factor 1 over a cube because, of course, the energy density of relativistic fluid goes like, if you think of it as the energy, I mean, a loose way divided by the cubic value of the A, the volume, okay? And the energy, of course, goes like, let's say, h nu of a photon, which is traveling with a given frequency, divided by a cube. But remember that the universe is expanding, so the frequency goes like 1 over a, because it goes like the inverse of the length of the wavelengths, so it goes like 1 over a cube. So let's say a divided by a minus 1 divided by 3, so it's 1 over a4. Okay, so you have to take into account that the photon is redshifted. Okay? Now, in the case of a non-relativistic fluid, which is the matter-dominated period, you lose this extra factor of the frequency. So in the matter-dominated universe, MD, you have that P is basically zero, not exactly zero, but zero. We can take it vanishing for the time being. So W is zero. And then, of course, the equation is rho dot plus 3h this time, because there is no pressure, rho equal to zero, and therefore rho goes like a to the minus 3, which you expect to be typically the mass of your particle divided by the volume, which is exactly this behavior here. Okay? There is another solution that I would like to, because of course it's important for inflation. The other solution is the case in which it's called the sitter, which is rho equal to minus p, so W equal to minus 1. And in this case, funny enough, as you see from the equation, rho dot is equal to 0, so rho is constant as a function of time. So it's a typical case in which the energy density of the universe, despite of the fact that the universe is expanding, does not reshift away. And that's exactly what we are going to use for a period of inflation. Okay, so those are very standard kind of introduction. Let me see if I miss something. To some extent, yes, because I want also to tell you the corresponding scale factor behavior. Okay, so let's go back to radiation. In this case, if I have a radiation-dominated universe, once I have the behavior of rho with a to the minus 4, you can go back to, for instance, to this equation here. One of the three, in fact, you're going to get the same result. And then you get the scale factor goes like the square root of time. Okay, in this case. It's easy to prove it, so I let you done it. In the case of matter, the behavior is not exactly the same. You get A of t goes like t to the power 2/3. Okay, so the universe is expanding in a different way. And then finally, in the case of the sitter, what you have is the fact that since rho is constant, so if you look at these equations, of course, the second one, you're going to get that A goes like exponentially with time. So with some constant, which I put h star here, for instance, to remind me that it's a constant times t. So it grows exponentially. Okay? So those are the behavior that I will be focusing from now on. And again, I to some extent, I take it for granted. All right. Now, let me go back to this equation here. You notice, in fact, that when I go back in time and I follow the behavior of the energy density, what is winning when I go back in time, when the scale factor goes to very, very small values, I have a to the minus 3 for the matter domination, and a to the minus 4 for the radiation. So it's clear that when I go back in time, 1 over a4 is winning. Okay? It's winning also compared to the a square here that I have in the first equation. So it's clear that unless something very funny is happening, when I go back in time, I can neglect the curvature term, even though now I will go back to it and give it a very fundamental importance. But for the time being, just learn the fact that when I go back in time, rho goes like 1 over a to the 4th. This goes like 1 over a square. So it's clear that when I go back in time, we have a very good reason to believe the universe was dominated by radiation. Okay? And of course, during the evolution of the universe, there will be different phases. For instance, there will be a transition from radiation to matter. In fact, Matteo will propose you an exercise about it. And then eventually, as we know very well now, lately, we are dominated again, apparently, by a dark energy, something like that makes the universe accelerating. So we are entering more or less in this phase here of the Sitter period, where rho tends to be negative and almost equal to the minus pressure. But we are interested in what happened at the beginning of inflation. So we are going to discuss what, when the universe seems to be dominated by radiation. So I will forget for a time being the matter and the dark energy. Okay, it does not concern us anymore. Okay, so that is something that you learn from the first equation here in the list of three. Of course, again, when we go back in time, you might worry about the fact that there is a 1 over a to the fourth, so at some point the energy density explodes. Of course, the singularity, the Big Bang, blah, blah, blah. But then from the point of view of inflation, as we will see, the Big Bang has no meaning. Okay, so there is no, we are not interested, if inflation took place, we are not interested in the notion of Big Bang, because in fact, inflation will erase all the informations that took place if there was something before inflation. So in any case, for us, from the inflationary point of view, the Big Bang is the moment in which inflation ends. Okay, it's the moment where radiation is produced, as we will see, and then any information about the singularity is in any case erased, and there will be no experiments able to detect anything about the Big Bang. So in any case, it's a notion that is only kind of philosophical in this kind of picture. Okay. All right. So now, having done a little bit of summary, let me go to the notion of the horizon, because it's important from the inflationary point of view. So, okay, so far? Too fast, too slow, boring, criticism, nothing. Okay, good. Okay, so let me go to the notion of the particle horizon. So what is the particle horizon? Is the maximum distance a photon can travel in an expanding universe. And since there is nothing that travels faster than light, as we know, it's really the maximum distance by which I can communicate information from one point to the other. So how I get it? I take the metric, and you know the equation of motion is ds squared equals 0 for a photon. Okay, so this is for the photon, or for any massless particle, in fact. So even the graviton, for instance, but let's focus on the photon. So in this case, what I have that minus dt squared plus a squared of t times dx squared has to be equal to 0. And therefore, the physical distance, which is, because from here you get the dx is equal to dt, let's say dx in modulus is equal to dt over the scale factor. Okay, this coordinates x is called co-moving. Okay, but we are interested in the physical distance. So the fact you have to take into account the fact that the universe is also expanding. So from here, I can integrate over time this object here, and I define the particle horizon Rh of t as the scale factor times the integral from 0, let's say, from some beginning of times, whatever that means, in till t, or dt prime over a of t prime. Okay, so that's the physical distance that a photon can travel from the beginning of time, let's say from the Big Bang or whatever, to a given time t. Okay? Now, in a standard cosmology, this, as you can guess from the beginning, I mean, since we are dealing with and we are assuming that the velocity of light is equal to 1, you can guess that this behavior will give you something like r of h of t goes like t, so or c times t, the distance that the photon is able to propagate in a given time t. But if you do the computation, you are almost right, because suppose that a of t goes like t to the some power n, when I remind you n is equal to 1/2 for a radiation-dominated universe, is equal to 2/3 for a matter-dominated universe, okay? If you now plug this behavior, as I can tell you, you see, I never write down the full formula. I could have written down A of t equal to some A star, let's say A at the time t star, times t divided by t star to the power n. But I don't care, because in fact here, as I told you at the beginning, the A has always to enter as ratios, because A has no physical meaning, so only the ratios has physical meaning. So I only give you the behavior like this. If you do the integral here, what you get t over 1 minus n. Okay, so roughly t. We were roughly correct in suggesting that it goes like t. There is a small factor, 1 minus n, so it's a factor of, for instance, for radiation, this gives you 2t for radiation, which we are be interesting in. So in fact, because of the expansion of the universe, it looks that the distance propagated by a photon is larger than t. It looks that it's superluminal, but in fact it's not. Because of course, what is physical is what you measure. So you're not gonna measure this quantity directly, okay? You can also rewrite this particle horizon in another way. Let me rewrite it in a slightly different way. So if you take the dt over A, and you rewrite it as dt over dA times dA over dt, so it is equal to dt over dA. Sorry, I forgot A here. So dt over, let me redo it. So dt over A, I write it as dt over dA times dA over A, okay? And this piece is A dot, or if you like, 1 over A dot, okay? So you can rewrite the horizon, the particle horizon, as A of t times the integral in dA over the scale factor times h, where this h comes from directly from this A dot. I multiply up and down by A, and I get this, okay? So this quantity, 1 over AH, is called the Hubble radius. In fact, it's called the comoving Hubble radius because it's divided by 1 over A. If I remove the 1 over A, it will be the physical Hubble radius, okay? Now, notice that let's focus on the physical. So I remove the 1 over A. I don't take into account the expansion of the universe, so I have 1 over H. So it's called the Hubble radius. Okay, what is this 1 over H? Let's suppose that, let me change again the blackboard. So in standard cosmology, this 1 over H is almost the particle horizon. Okay, so 1 over H is called the physical, if you want, just to specify that your physical quantities, Hubble radius. Okay, and what is it in standard cosmology? Let's take a radiation-dominated universe. We know that A goes like t to the power 1/2. Okay, so A dot goes like 1/2, t 1/2 minus 1. Okay, and H to the minus 1, so H will be from here 1/2 over t. Okay, and you see that H minus 1 will go like 2 times t, which is exactly the particle horizon. Okay, from if you put n equal to 1/2 here. So in standard cosmology, the physical Hubble radius is the particle horizon. You don't care to distinguish between the two of them. And in fact, in the articles, sometimes you find the notation Hubble radius, sometimes you find the horizon. There is no reason to distinguish them. But during inflation, or during a period of the sitter, because as we will see, the period of the sitter is basically inflation, what happens is that these two quantities will be dramatically different. Okay, so let me do a computation now, a very easy one. I can erase, I think here. And that's the basic first information about inflation that I will like to give you. So if you compute particle horizon, the distance that a photon propagates in a de Sitter period, so let's say that rho is equal to minus p. Okay, so equation of state W equal to minus 1. We know that the particle horizon is A of t, the integral from 0 to t, let's say, of dt prime divided by at prime. Okay? And let's suppose that there is a period, I will show you that there is such, that the equation is such that A of t goes like, this time let me write it down, all of it. So I write down A of t star, some time, let's say, or some initial time, if you like. And here I put some ti, just to not to identify to 0. It will be the beginning of inflation, let's say. And then I have e to the h star, some constant, t minus ti. Okay, so let's suppose that the universe for some period was expanding exponentially, very, very fast. If you compute this object, so here you will have a of ti, e to the h t minus ti, and then times the integral from ti to t of d t prime divided by a of ti times e to the minus h star t minus ti. Okay, so you see here the ti goes away, as it should be. Okay, and then I have the integral. So let me write it here, so it's a little bit of a mess, but the integral can be easily done because it's just an exponential, and then what you get at the end, you get e to the h star times t divided by h star in the limit in which t is much larger than ti. Okay, so you get an exponential growth of the particle horizon. Okay. On the other side, what about the Hubble radius? The Hubble radius is h to the minus 1, which is a over a dot. But in this case, this is nothing else than h star to the minus 1. It's just a constant. So you see, during inflation, as we will see, the particle horizon is much larger than the Hubble radius, which is a constant. It remains constant. So what is the meaning of the physical Hubble radius? Remember that you have this integral in in dA over AH. So what is the physical meaning of this 1 over h, or the comoving if I divide by a? Imagine that the universe has expanded in such a way that the scale factor has changed by a factor of unity. So dA, if you like, I take a dA of order of a, okay, so the relative changes of order of unity. So it means that this is, the Hubble radius has the meaning of the distance propagated by light when the scale factor grows by a factor of unity. Okay, but the particle horizon is in fact the distance from the beginning to a given time. So you give all the length of time available, so the whole period of inflation, it goes much larger than the Hubble radius. You see, this is exactly the Hubble radius. So you see that it's much larger than the Hubble radius. So in standard cosmology, you don't care to name one or the other. In inflation, you have to be extremely careful to tell what is the Hubble radius and to tell what is the particle horizon. And that's, in fact, one of the key reasons why inflation is so important, because what will happen is that during inflation, light will be able to propagate a very large distance in such a way to solve what I'm going to tell you about in a few minutes, the so-called horizon problem. Okay, so that's a very important difference between these two notions. questions about this? Okay. Or yes. Where? In the physical labor radius. So this one. Ah, the R. Ah, here you mean? No, here. No, that's the, so the, it's co-moving. Yeah, so it's, I think it's correct. Yeah. So you're looking at this part. Ah, okay, good. So just because with 4 blackboards, it's difficult to. Okay, tell me. Ah, yeah. But here, yeah, of course. But here I'm just looking at the behaviors, so it's okay. Yeah, okay. The final formula, it's okay. Yeah, sure. Okay, very well. So now let me go to the problems of standard cosmology, which we start with. So there are 3 of them. So let me raise again. I think can I raise that one? All right. So let me go to the problems of standard inflation, standard cosmology. Yes. Yes.
It's 1 over a dot. So if you want to define this as h, you have to do h squared.
No, I'm not convinced. But anyway, yeah. Statement during the lecture, I will forget factor of 2, spies, and so on. Okay, that's for sure. But focus on the physics, not on the factors. Okay. Let me go back because now you are bothering me. Wait a sec. So you are claiming that there is a square here? You're now bothering me because then either I've been teaching for years wrong. Yeah. Wait a sec. So wait a sec. I have the physical. So a of t times the integral in dt over a. You agree on that? So it's a, okay. Let me call it RH. A of t. You might be right, eh? dt over a. So I write it as dt over dA over a. You agree? You agree on that? Right. So now is the integral in dA over a. And here I have 1 over a dot. Okay, right? You multiply by a, and a. This is 1 over h. Yes, because stupid. You're right. Because here I put a d log of a. Yeah. Sorry. I forgot. Because for me, in my mind, d log a is over a unity. So you see, physics, not mathematics. But you are totally right. Good. Very good that you're very much awake. Eh? Yeah. Because in fact, I wrote d log of a. So the formula will be integral d log a of h over a. Okay, that's the reason why I was telling you that this is factor of unity, in fact. Okay, never mind. So problems of standard cosmology. Okay. So what are the problems? There are 3 problems that I would like to tell you, even though 2 of them are rephrasing the same one. I will give you two different ways to see the same problem. So the first one is the so-called flatness problem. It's not really a problem in the sense of inconsistency of the model, but as you will see, it's a kind of, sometimes it's also called a fine-tuning problem, because of the numbers that will come out. Okay, so let's start from the equation h squared plus k over a squared equal to 8 pi g Newton divided by 3 times rho. And as I told you, let's go back in time when the energy was basically dominated by, radiation. So from now on, we are considering only the period of radiation. Okay? Now let me introduce a parameter which is called omega, which is defined to be, so that's just a definition, it's not nothing particularly new. I just define this quantity to be rho divided by rho critical, rho c, where rho c is equal to 3h squared divided by 8 pi g Newton. So you see, I've done nothing. I just simply redefine a quantity in such a way that if k is equal to 0, this parameter k is equal to 0, I just solve the equation. And rho critical will be the energy density of the universe if k was 0. Okay, nothing, no, I mean, just some algebra here. Okay? So now I can rewrite this equation in the following form. Once I define this omega equal to rho divided by rho critical, I can rewrite this the h squared. Let me write it: h squared plus k squared equal to 8 pi g Newton divided by 3 rho. I can rewrite it as omega minus 1 equal to k divided by a squared h squared. Okay, so again, that's the first Friedman-Robertson-Walker equation. It's just a rewriting of this one, so there is nothing new. But the reason why I do it is the following. Now, suppose that I'm in radiation. So as we said, rho goes like a to the minus 4. So h squared will also goes like a to the minus 4, because in this equation, rho is dominated over the curvature term. So this guy will go like a squared, because it will be a squared, a to the minus 4, so you go to the numerator and it goes like a squared. Of course, if k equals 0, which is not the case we are interested in, so for the time being I'm supposing k different from 0, of course omega will be equal to 1 all the time, so we don't care about it. But let's focus on the case in which the universe is not exactly flat in its globality, okay? So because of this behavior, what I get that omega minus 1 at a given, let's take the modulus, at a given time t, divided by omega minus 1 at a time t0, let's say today, in modulus, will go like, and here again, I'm making an approximation because I'm forgetting the matter-dominated period. I just want to see, roughly speaking, what is going on, okay? So it will go like A divided by A0 squared, okay? So suppose that I take the value of omega minus 1 today, I go back in time, I forget about dark energy, which is in any case very short, I forget about matter, I assume that the universe is radiation dominated all the time, and I get this behavior here. So how do I now evaluate, from the quantitative point of view, this number? Now, I use another fact, the fact that as you know, the expansion of the universe is adiabatic, unless during a period of inflation, but here we are doing standard cosmology. So I'm using the fact that the entropy density the small s is called, of my universe, if you compute in a thermodynamical environment, is going to be 2 pi squared divided by 45 times the degrees of freedom that are present in your universe. For the standard model, it's about 100 or so. So this is about 100 times T cube. The important thing is that the energy, the entropy density goes like the temperature cube, okay? Like a factor of cube of the temperature, and the entropy, the total entropy, will go like the entropy density times the volume, okay? No, sorry, the other way. Okay, so what happens is that I have to remember that the entropy is constant. Here I'm also making another assumption. The total entropy is constant because there is nothing more isolated than your universe, in fact. So from here, knowing that the volume goes like a cube, and knowing that the entropy density goes like T cube, what I learn is that T times A cube is a constant as a function of time. So I learned that T goes like 1 over A, okay? Which is not surprising. Think about a photon, right? A photon, which is in thermodynamical equilibrium with its environment, with other particles, okay, has a typical energy, which is 3 times the temperature. And we know that the energy of the photon goes like 1 over A, so the energy goes like 1 over A, and the energy is T, so you get this. Why I'm saying that? Because of course now what I can use the fact that this is nothing else than T0 over T square. Okay? Yeah, of course. I'm assuming radiation dominated as I stressed many times. Yes. It's an assumption, it's just an approximation, but I just want to get roughly the numbers. So you see it goes like T0 over temperature. So now what happens is that I go back in time. The temperature is increasing because the scale factor is decreasing. And therefore, I can put numbers here. Now let me be very bold and let me take the temperature to be the largest one that I have in my mind, which is the Planckian temperature. So now I assume that that T is of order of m Planck, which is, as you know, about 10 to the 19 GeV. And I take T0, the temperature of the photon today. Okay, so this is the today temperature of the CMB, which is about, as you know, it's about 10 to minus 10 to minus 4 GeV, something like this. Sorry, 14 GeV, something like this. 14, 13, it's not relevant, the number, okay? So it's about a factor of, thank you. It's a factor of that order there, okay? So now, if you put, well, if you want the precise, it's more close to 13 GeV, 10 to minus 4 eV or something like this. Very cold CMB photons. So what you have to get is that this ratio, omega minus 1 at the time t, divided by omegas minus 1 to the time t0, if you put a number, is about 10 to minus 60 or 62, let's say 62 or something, okay? Or even smaller. So what happens is if you, in fact, you should put 18 here because that's a reduced Planck mass, but never mind. Those are very small numbers. So this is a very small number, okay? So, of course, I took here this number to be over a unity. We know that omega minus 1 today is very close to 0 up to some percentage. But of course, to take the ratio, I need to take some number over a unity. As you know, if I take 10 to minus 2, this number is so small that I won't lose that much, okay? So what is the flatness problem? Why it's called the fine-tuning problem? In fact, as you see, there is no problem from the rigorous mathematical point of view. But what happens is that in order to explain the universe as we see it today, we must have assumed that it started very flat. Okay? But ridiculously flat, like 1 part to 10 to the 60. So if you plot basically the behavior of this quantity omega minus 1, as you have seen, it goes like a square. So in order to explain a physical measure today, observable measurement, which is omega close to 1 in any case, but not exactly 1, in order to explain it in standard cosmology, so here you plot modulus of omega minus 1. Here, let's say that you put, or you plot the omega, let's say omega, and here you have 1. Okay, here is today. T0 is a function of time, or if you like the scale factor, let's put a scale factor, better. So this is A0, let's say. And then it's very close to 1 in any case. So you have to go back, let's say this is some initial time, let's say M Planck. You have to go back, 10 to minus 62 or something, in order to have an omega which is also close to 1 today. You have to squeeze the system very much. Well, you can say, well, who cares, right? My universe started in this way. He has some special initial condition, and we don't care that much. It's what it is. If you invent a mechanism, and people, of course, have done it, to explain why the universe was so flat at the beginning of inflation of the standard cosmology, then, of course, you are done. It's you will have a solution. What I'm going to tell you, maybe we could take a break now in a few seconds. What I'm going to tell you in the following, that in fact, what I will explain is to rephrase this problem in another way, to convince you that in fact, even though you invent a method to explain this fine-tuning, you will have troubles anyway. And then I will go to the horizon problem to explain to you why, in fact, even though you solve this problem, you're not done at all, and that's the reason why inflation will come into the place. Okay, so let's take a break. Maybe I don't know, a coffee time, as in Italian, 5-10 minutes, and then we will resume. All right, can start. Okay, so now what I want to, as I told you, I want to rephrase the problem and make it an entropy problem. So let me rewrite this equation, omega minus 1 equal to k over a squared times h squared. And now let's suppose that during radiation, I know that h squared goes like rho, as we said. And rho for radiation goes like the temperature to the fourth, because if you remember, it was going like 1 over a to the 4. Okay, but then we said that T goes like 1 over A, so I can take, of course, the energy density of a fluid in equilibrium goes like always temperature to the fourth. Okay, so now I'm doing something very, very smart. What I do, I rewrite this equation as K over A squared. So I have basically this behavior T squared, T to the fourth. And of course, here, by dimensional reason, I have a G Newton, which I write down as M Planck square. Okay, just to have dimensions correct. So here I have an M Planck square as well. Right. Then what I do something like this. I rewrite this equation in the following way. I collect the temperature and the scale factor here, and I divide by T squared. Okay, something very simple. So now I remember that the A times T is the factor that enter in the entropy, as we have seen. So what happens is that the entropy, the total entropy, so not the energy density, entropy density, which is small s. Here is a big S, which goes like small s times a cube, as we have seen, which gives rise to the fact that at is remains, roughly speaking, constant apart from the degrees of freedom. So what happens is that this guy will go like a times t cube. So here I recognize the same power. So what I can rewrite, let me go here, omega minus 1 will be k over M Planck square divided by s to the power 2/3 times t squared. Okay? Now, and this is the key point. I go back in time, and now I use the fact that my universe expands in an adiabatic way. Okay? So what I do here, I simply rewrite this ratio, but this time, since the capital S is constant, I can rewrite this as S0, the value that he has today to the power 2/3 times t squared, where S0 is the S at the time t0, let's say today. Okay, because I'm using adiabaticity. Okay, that's the key passage. As you see, there is nothing really ingenious, mathematically speaking, but the physics is here. So now, what is the entropy of my current universe? Well, it's let me estimate it in a very simple way. S0 will be the temperature that I have today, T0, as we see before, it's 10 to minus 14 GeV, times H naught 0, which is the maximum distance I can probe today, which is my horizon today, which is about 6,000 megaparsec, which in units, in natural units that I was introduced before, this is something like 10 to the 42 GeV to the minus 1. Okay? So this number here is, if you now put the 10 to the 0, T0 like 10 to the minus 13, is like 10 to the 90, okay? Forget about 91, 92, that's not important. I get this number here. And now if I compute this number at t equal to m Planck, as we did before, you get again 10 to minus 60. Okay, before we get 62, but never mind again. So you see, the flatness problem is in fact an entropy problem in the sense that we have to explain why the universe was born with a huge number of degrees of freedom. Okay? And it's also clear, if I rephrase the problem in this way, that a way to solve this problem will be to get rid of this. Okay? That is the way I think it's more interesting to see this flatness problem. It's a problem due to the entropy. How do you produce a large number of degrees of freedom in my universe? And how do I violate, for a short period of time, adiabasicity, which is exactly what inflation will do for you. Okay? So that is the way you have to see about this problem. All right, so nothing is still done from the point of view of the problems, because of course, again, you can imagine some phase transition, something, so you can say, well, I don't care about this initial condition, the universe was born here, was born like this, don't care. But now I'm going to tell you something much more interesting, something that you cannot get rid of, which is really the key point, the key fundamental reason why inflation has to be invoked. In fact, we will now approach the definition of inflation, which is the horizon problem. And that's the reason why at the beginning I was so stressing about the definition of the Hubble radius and the definition of the particle horizon. Okay, so let's look at what is the horizon problem. The horizon problem is something that you can easily understand if you go back in time again in the following way. In fact, it's just let me just show it from one picture, which is quite illustrative, even though I don't draw very well. Let's put here on the horizontal axis the log of A, the scale factor. Okay, so let's use these units, and here I put the log of some distance that it depends on the one that the horizon or wavelengths and so on. Okay. All right. So now let's plot some wavelengths, for instance. A wavelength lambda goes like the scale factor. Okay. So the universe is expanding. Any length grows like the scale factor. Or think about the distance between 2 points. Of course, physically, the universe is expanding, so I have the co-moving distance times the scale factor. So here what happens is that the log of this will go like log of A. Okay, so this is log of lambda will go like log of A. So it will be a straight line with a steepness equal to 1 in this plot here. Okay? How about h to the minus 1? H to the minus 1, we have learned, goes like, it depends, let's take radiation for instance. We know that h during radiation goes like, h squared goes like 1 over a to the 4th. So h goes like 1 over a squared. So h to the minus 1 will go like a to the 2. Okay, so the log will have a behavior like this. Will have a behavior like this. So let me use the dashed line to put the log of h to the minus 1. And here again, I don't care about particle horizon or Hubble radius because, as we said, in standard cosmology, they are exactly the same, more or less, apart from a tiny coefficient. Okay? So you see the steepness of the two functions in this plot, they are different. And the horizon or the Hubble radius is faster when I advance in time compared to any physical distance. So sooner or later, if I have a distance between two objects, like see a distance between two galaxies, which of course I observe, so they are beneath the Hubble radius, I can see them. So let's say that I have a distance which is smaller. Okay, so this is, I put my distance smaller than the horizon today because I can observe things. Sooner or later, when I go back in time, this distance will become smaller and smaller, of course, because I go back in time. But the horizon goes even smaller. Okay, so sooner or later, that distance becomes larger than the Hubble radius at a given time. At some point, the two lines have to cross because the steepness is the same. The same is also true for matter because if you remember, it's a to the cube, so h minus 1 goes like a to the power 3/2, which is larger than 1. Okay? Of course, so now you ask yourself, why is that a problem? If I look at 2 points, sooner or later this point, they go above the Hubble radius. They are not connected causally. So what is the problem with that in principle? The problem with that is that we have observation that, in fact, reveals that this picture is wrong, cannot be correct. Or we have reason to believe that it's not correct. Why? The reason is, of course, that we observe photons from all over the places, which is called the cosmic microwave background radiation. Or CMB. Okay, so we observe photons if you take a sphere, and we are here, let me put, this is us. We are obtaining photons that comes from the early universe, from all over the regions. Okay, so at basically 2 pi. And the temperature of these two photons is about, as I declared before, is about 10 to minus 13 GeV, sorry. So very, very cold photons. And we observe them from all over the places. So if I look in this direction, I obtain photons with a very accurate detector of this temperature. If I collect photons on my back, they're going to have the same temperature, up to very, very, very small fluctuation, delta T over T0, which is about 10 to minus 5. So when I collect photons and I measure them, the temperature is roughly the same apart from this 10 to minus 5. Now, this 10 to minus 5 will be the goal of the explanation for the last 2 or 3 lectures. So for the time being, we forget about this. We assume that the delta T over T is 0. So the photons have the same temperature for the time being. Okay, so now, so here I get a photon that today arrives with a temperature T0, here with the same temperature T0, here with the same temperature T0. Okay? Now, let's go back to this picture. Suppose now that I'm here, this is today. Okay, I collect photons And of course, the distance of these two photons when I collect them, suppose that I take a given angle, okay? When the photons arrive to me in my detector, the typical distance between these two photons will be simply the size of the detector, okay? But now let's go back in time, and I want to ask myself when these photons were emitted, okay? So, and now I have to face this kind of picture, because if I discover that these two photons were emitted, for instance, in this range of time, then I have a problem, because of course these two photons that I receive, for instance, from this place and this place, I measure them here, these two ones, okay? I discover, and now I will do a computation to in fact to see that it's true, I discover that in fact they were emitted where their distance was larger than the Hubble radius. Okay, so when they were emitted, these two photons were not causally connected. There was no reason why they had the same temperature. You see? So the question is why the temperature of these two photons that were emitted from region where the Hubble radius was smaller than the distance between them had the same temperature. There is no reason. They were living in two different separated universes. Why they should have a temperature with the same temperature up to, as I said, 1 over 100,000. Okay, so that is the horizon problem. Now let me do a computation to show. In fact, this is because you might have seen, well, they were emitted here when the two lines were switched, but in fact it's not. This is the case. Okay, they were emitted where they were not in causally contact. And now let me show how this comes about. Let me do a very simple computation to show that in fact these photons were very much separated when they were emitted. This is the goal of this computation that I'm going to do now. Is that clear, more or less, the problem? Okay. Now let me be a little bit more quantitative, because when are the photons emitted, so to speak? What is the time of emission? The time of emission is the so-called last scattering surface, or last scattering time. Okay? So during the evolution of the universe, the photons are, of course, interacting with the fluid around, which is made of baryons and electrons and ions, of course. So at some point, when the universe starts, the universe expands, and of course the distance between the particles increases. And of course, for the photons, it's less probable to encounter particles around, because of course the distance between them increases. So at some point, how do you produce photons, for instance? At some point you have processes like proton, which meets an electrons, and it goes back to an hydrogen plus a photon, okay? Of course, the photon is interacting only with charged particles, but that's the typical process that we can look at. So during the evolution of the universe, of course, it's easier at some point to go into one direction compared to the other. And if you do a simple computation, you use basically standard electrodynamics. What you discover is that during the evolution of the universe, this process goes out of equilibrium, so it starts happening. Sorry, it stops happening. Let's say equilibrium. At the temperature, which is, let me call it last scatter, okay, LS, of order of 0.3 eV. Okay? So how you can estimate this number? Well, you take the cross section of this typical process. You multiply you take the free mean path of this process, and you compare it to the Hubble radius. Okay, it's as simple as that. I don't have time to do the full computation because it's quite detailed, but roughly speaking. It's surprising that the temperature at which this process stops taking place is not order of 13.6 eV, which is the first energy level of the hydrogen, right? So you have an hydrogen with the first level. you send the photon, you can ionize with hydrogen, you can liberate the proton and the electrons. But in fact, you might expect that, roughly speaking, you should expect a temperature like this, but in fact it's a factor of 10, larger or so, or even more. And the reason is because, of course, in the universe, you have many more photons than protons and electrons, okay? So every time you want to create an hydrogen, it's going to be destroyed by the photon because there are so many around it that is going to easily be destroyed. And you have to reach a temperature which is much colder than the first energy level of the hydrogen atom to stop this kind of photo dissociation of the hydrogen. Okay, but the moment in which that happens, which is about this temperature here, what happens is that at that time, the photon stops basically interacting with the surrounding matter and starts propagating completely free, and the universe becomes transparent to photons, okay? That's the moment where you create the CMB. In fact, when you take the picture of the CMB, when, if you think about experiments like Planck or older experiments, in fact, what happens is that you see this CMB photon sphere, let's say, and that is the picture of the universe when the temperature was about a fraction of the electron volt. Okay, you cannot go farther in time, back in time, because of course at that time the photons were so much interacting with the surrounding matter that in fact the freeing path was very small, and therefore it was, they cannot propagate to us freely. So that is more or less the time that we were going to choose in order to explain this thing here. Okay. So now, having said that, let's compute how many Hubble volumes, how many particle horizon volumes there were at the time of last scattering. So this sphere here is in fact the last scattering surface. Okay, so if you imagine that you are surrounded by this sphere, you go back in time, at some point you hit the last scattering surface, and the photons were emitted basically almost free and they arrived to us, here at the center, they propagate over the universe almost untouched. Of course, they are not completely untouched because, of course, they travel sometimes galaxies and so on, but those are rare events. So for the time being, we assume that they are arriving to us, carrying the information they had at the last scattering surface. Okay, so how many volumes I have how many Hubble volumes I have on this last scattering surface? So I want to compute now how many of these small volumes, so those are h to the minus 1 and last scattering, how many of them I have, and I want to see, in fact, if the Hubble radius was smaller than the sphere or larger, if I have an horizon problem or not. Well, let's take out the typical distance to be h0 to the minus 1 today. So this is today. Okay, and I want to go back in time. So let's maximize. In fact, let's try to minimize the problem. Let's take two photons that arrive from one point here and the other point at pi, okay, from here. Okay? Of course, I take a photon that comes from one direction, I take a photon that comes exactly from the opposite direction. So the distance is about the horizon, my universe, okay, today. So I take this, and then, of course, how it will get back in time, it will go like this. I have h0 to the minus 1. Then I have to multiply by the a at the time of last scattering divided by a0. Okay, so that is when I reshift it back to the time of last scattering. On the other side, we know that since the temperature is about, as I said, the temperature is about 0.3 eV, this is more or less the time at which the universe becomes matter dominated. Okay, so let me take a simple. I deviate from the assumption that I do all the time, that I assume a radiation universe. This time I have to assume a matter-dominated universe because I go from today to the temperature which is about 0.3 electron volt, which is more or less at the temperature at which the matter domination starts. So this time I go using matter scaling, the matter dominated scaling. So we remember that h minus 1 goes like a to the power 3/2, okay? So it means that h minus 1 at the time of last scattering is equal to h0 to the minus 1, so the time today. And then, of course, I have a last scattering divided by, okay, let's put a at t last scattering, divided by a0 to the power 3/2, okay? So that is the Hubble radius when the universe was at the temperature of about 0.3 eV. Because during this period, to go from today to that temperature, I have to use a matter-dominated universe. Okay? So now when I take the ratio of these two quantities, so I have taken my universe, reshifted back to the last scattering. I take my horizon, computed the last scattering, and what happens is that I have this ratio, lambda at t last scattering, divided by h minus 1 at the time of last scattering, is going to be a0 divided by a at the time of last scattering to the power 1/2. But this is nothing else than the temperature of last scattering divided by the temperature today, because I use the fact that T goes like 1 over A, okay, to the power 1/2. Okay? This is what is, let's say an electron volt is 10 to minus 9 GeV, so I get 10 to minus 9 here. T0, as we said, is 10 to minus 13 to the power 1/2. So this is 10 to the 4, and this is 10 to the 2, more or less. Of course, if I take the cube of it, because I want to take the volume, I will get 10 to the 6. So meaning that at the last scattering surface, let's only focus on the line, for instance, just to make an example. Of course, we have to think in terms of a sphere, but let's take a line. It means that the two photons that were separate, that I get from one direction, the opposite direction, were separated, okay, but by about 100 horizons. Okay, so there is no way they could talk to each other, meaning that in fact the situation is the one that I drew. So if I put here the last scattering, the situation was the fact that the photons, even though they are collected today by my detector, they are of course beneath the horizon. When they go back in time, their distance was larger than the Hubble radius by a factor 10 to the 2. Okay, in volumes 10 to the 6, of course. Okay, so the question is, why do they have the same temperature? There is in principle no way to make them talking to each other to have the same temperature up to a precision of 10 to minus 5. Okay, so that is the called horizon problem. So it's contrary to the other problem, the fine-tuning and so on, which looks more a mathematical problem. This is really a physics. We have an observation that contradicts the way I construct the history of the universe according to standard cosmology. I don't know how to deal with this problem if I continue to be stuck to the standard cosmology picture. Okay? Questions about this? Is that clear? Okay. Of course, I could even go back more in time. I could go to nucleosynthesis period where the temperature was much larger when the first light elements abundances were formed. The problem will become even more serious, because if you go back in time even more, if I have observation, then of course the distance between these two lines will be even wider. But of course, this is sufficient to state the problem. All right. Okay, so now, having said that, let's go to start talking about the real stuff, inflation. So, how do I solve this problem here? How do I solve the horizon problem, the most serious problem that I have? Okay, well, one way to do it is, of course, to change the lines, the behavior of the lines. So one is, of course, the fact that the distance scales like the scale factor. So the fact that log of lambda goes like a log of A, that I cannot change, because that is really due to the space-time geometry. Any wavelength will go like the scale factor, so that I cannot change. But what I can do, I can change the behavior of my horizon. Suppose that I go even more. if I now have a way to make the Hubble radius changing in a way that you recross the line, okay? I have to be smart enough to change the Hubble radius and to recross the line. Then, of course, if I cross it back in time, I can have a way to solve this horizon problem, because I can say that back in time, what happens is that the photons were causally connected in this region. They talked to each other. They told them, well, look, we have the same temperature. Then they went out of the Hubble radius, and then they re-entered today with the same temperature, but because they had at the beginning. You see? It's a simple graphical way to solve the problem, but of course now I have to tell you how to make this change in the Hubble radius. But in principle, you can do it. So photons have the same temperature today, according to this graphical solution, because they were talking to each other, they were in causally contact at early epochs before the last scattering, okay, back in time. So what is the mathematical requirement to, from the point of view of mathematics, how can I impose that this crossing takes place? Well, I have to simply impose that the ratio between lambda and h to the minus 1, the derivative with respect to time, okay, is larger than 0. Okay, so the ratio has to increase, or when you go back in time, if you like, to decrease. But lambda goes like a, h minus 1 goes like a divided by a dot. So this is true only if a double dot is larger than 0. Okay? Yes, thank you. So it's larger than 0. So you see here, this is the definition of inflation. So inflation is defined to be the period for which a double dot is larger than 0, period. That's the definition. Okay, how you get this period, you don't care that much. All right? So that's what we are supposing. If there is a period during the evolution of the universe where a double dot is larger than 0, which we call it inflation, then of course you can recross the line back in time in such a way that the photons were causally connected. Okay? Now, suppose that I want to solve the horizon problem, and let me do a computation, and then eventually we will stop. So, what numbers do I need for inflation to last sufficiently enough to solve this problem? Suppose that you have a period of inflation, and for the time being, so let me do an assumption. Let's suppose that a double dot is larger than 0, so I have a period of inflation, and also let me suppose that I get it when p is equal to minus rho. Okay? Because if you remember, a double dot divided by a was minus 4 pi g Newton divided by 3 times rho plus 3p. If p is equal to minus rho, I have minus 2 pi, rho here. Okay, so minus times minus is plus, and I have a double dot larger than 0. Okay, so for the time being, for simplicity, let me assume that a double dot is realized by p equal to minus rho. I will tell you how to get it later on. But for the time being, let me suppose that is true. So if it is true, then of course, as we said before, h squared is of order of rho, which is a constant. Okay, because of course you remember also that rho dot plus 3h rho plus p was equal to 0. So if I have rho equal to minus p exactly, rho dot is constant. So rho dot is 0, so rho is constant. So the scale factor goes like e to the h star times t minus some ti. Okay? So it goes exponentially. And now let me define a quantity, which is the number of the n. It's a number of e-folds. which tells you basically how long inflation is lasting, but in some particular units, because I define to be this n to be h t final minus t initial. Okay, roughly speaking, is the time at which inflation lasts, for which inflation lasts, times the Hubble rate, which is a constant, so I put an h star here. Okay, so I can rewrite this a t final will go like e to the n. So I take the number of efforts to be such that e to the n is how much the scale factor grows. Okay, it's just a definition. It's convenient to use this number of efforts. So now what I want to do, I want to solve the horizon problem, and I impose basically that when I go back in time, there was a period of inflation, not only of radiation or matter, but also a period of inflation in such a way that I impose the following. I take my initial Hubble radius today, okay, like I did before, and then this time I want to rescale it back in time, okay? So this is my Hubble radius today, h0. And then what I do, I do the following. I go to the end of inflation, so I multiply by AF divided by A0. So this AF is the scale factor at the end of inflation. Okay? So I take A0, the scale factor today, I rescale it back to the point of at the end of inflation. Then, of course, I take also a period where inflation is happening. So I multiply also by AF divided by AI. Okay, so AI this time is the initial. So it's the same fact at the beginning of inflation. All right. And then I impose what? I impose that this number is smaller than the Hubble radius at the time of inflation. So I want to squeeze my universe today inside the horizon, or better to say inside the Hubble radius, in such a way that all my universe today was in causal contact at that time. You see? If I do that, I've solved the problem. Because all my universe, at least the universe that I observe, was belonging to only one Hubble radius volume. So everything was in causal contact at that time. All right? So what is this number? So let me go here. So I will get h0 to the minus 1. So AF over A0, let's suppose that the universe from today to the inflation was radiation dominated. Again, I go back to this assumption. So I get T0 over Tf. Okay? And then this number is e to the minus n. And it has to be smaller than the value that I have, or the Hubble radius at that time. Okay? So you see, the trick of inflation is to give you a very, very small a very large contraction because of this exponential factor. Okay? So so again, T0 is 10 to minus 14 GeV, the temperature of photons today. The temperature at the end of inflation, we don't know it, okay, because it's a parameter that depends on the model. Let me just forget it, because I can rewrite this condition as e to the n larger than h0 to the minus 1 times t0 over tf times h star. And when I take the log, I get n larger than, of course, the log of h0 to the minus 1, t0 over tf times h star. Okay, so it's, of course, it's a dimensional number. But let me just look at this number here. Okay, so let me look at t0 times h0 to the minus 1. If you remember, h0 to the minus 1 was 10 to the 42 GeV. T0 was, as I said, 10 to minus 13 GeV. And let's assume that for the time being, h star is of order of Tf. Just to simplify, in any case, I'm not going to make a big error because it's a log. So here, what I get a number which is about 60. okay? If I take the log of 10 to the 42 times 10 to the minus 13. So what happens is that the number of e-folds that by which the universe has to expand during inflation is about 60. In order to, as I said, all my universe today to be squeezed in at the end of inflation into a region that was as small as the Hubble radius at that time. If I'm able to do it, then of course I have solved the horizon problem because all my universe will be in causal connection at that time. So this number here is not, of course, to some extent, inflation, what it's doing for you is to take the logarithm of your problem, okay? And then it makes numbers a little bit smaller. Before we have this 10 to minus 60. Now we have 60 or 62, or depends on these parameters, of course. So here I'm a little bit not very precise. But that will be enough. So if you have a period of inflation where the scale factor grows by a factor e to the 60, the horizon problem is solved. Okay? And what I'm going to do tomorrow, because I think now I'm done, I will show you that, in fact, these numbers here, the 60 is exactly the same number by which you solve the entropy and the flatness problem that I described before. Okay? I'm going to start the lecture tomorrow with a simple computation, showing that it's not a coincidence that you get the same number, and then I will tell you how to get, in fact, this equation of state. And from there, you will really start to do inflation. The background, as I said, I will tell you how to get inflation in the standard way. And then I will make things a little bit more complex. I will go to the perturbations, and I will tell you why this simple period of inflation with this scale factor going like this is, in fact, responsible for the structure and the anisotropy we see today. I will tell you how you can interpret on large scale, cosmological scales, the structure we see in a universe. I will tell you how they come from the microphysics, from the quantum fluctuations that you have during this period. So in fact, what you observe on large scales is in fact due, in this picture of inflation, to the quantum phenomenon and dynamics at very, very small scales. All right? So that's more or less the plan. Thank you.